welcome back to 15-Minute Math. So today we're going to talk about accumulation functions. So accumulation functions are, I think, a little bit non-intuitive when you first encounter them, but we're going to hopefully try to demystify that. So let's write an accumulation function on the screen here. We have g of x is going to be our function, and here's how we define a typical accumulation function. We'll define it where the lower bound of this definite integral is a, the upper bound is x, and we have some function here. We'll just have the variable t. It's kind of a dummy variable. It doesn't really matter what variable we put in there. And so this is the way you kind of see these accumulation functions, although it doesn't have to be the upper bound is x. You could have something like this. You could have your lower bound be a variable as well. But anyway, we're thinking about how much area is accumulated under this given curve. So f in this case is going to be the curve that we are concerned with. And just remember that this symbol here basically just means find the area between these 2 points. So that would be the area under f from a to x. Okay, so as an example, if I wanted to find g of 4, what that would kind of mean conceptually, that would be the area under f from a, and we'll just have to set a to be whatever constant value that we'd like. So the area under f from a to 4. And so you could say, well, let a equal 0, and then we'd just be finding the area under that curve from 0 to 4. Of course, it doesn't have to be 0, but it seems like 0 is a convenient choice in a lot of instances. But of course, it's context dependent, so a could be whatever constant value you like it to be. But it is a constant. I don't want to specify what it is right this moment, but when I'm going and I really want to define this function, I'm going to set a to be an actual, set number. And then x is a variable that's free to vary. All right, so we call it an accumulation function because we kind of imagine it accumulating more and more area as we let x kind of go down the real number line. To me, this is a very visual way to define a function, and so let's go over to Desmos and kind of see what's going on here. So if you look at my equation list here, g is our accumulation function. I don't have g graphed. This is not the graph of g. This is the graph of this 1/4 t squared. So you can see here in blue, f of t, 1/4 t squared. I'm graphing the function that we're concerned with, that we're finding the area under. For right now, I'm setting a to be 0. So what g is going to tell us is how much area is under this parabola from 0 up until, who knows, right? X, it's a variable. So what I'm thinking about, we call it an accumulation function because as x gets bigger and bigger and bigger, I'm accumulating more and more and more area, and you can see in red there, that's kind of what I want to think about when I think about these accumulation functions. Okay. Now, let's say I wanted to find a function value. Let's see here. Let's say I wanted to find g. Well, that's what we did on the last page. We wanted to find g of 4, right? Well, actually, here I've got my area too much. If I'm finding g of 4, then we're just finding that area there. How much area is under there? And of course, we could do that with a definite integral, because now that I know I want g of 4, I no longer have a variable here. It's just a normal definite integral, and Desmos does that for us just fine. It's 5.3 repeating. But you can see, if I do g of b, which is set to 4, I get the same thing. So literally, g is spitting out areas. How much area is under that curve? Okay? And so what would be interesting is to think about what the graph of G would look like. So we're starting at 0. So if I think about starting our graph of G at 0, I have no area accumulated whenever I start at 0, and I'm thinking about x equals 0 because my length times width, my width is 0. So my G graph is going to be at 0, 0. And then as x increases and we go to the right, notice that as we move to the right, we're accumulating positive area. But we can say even more than that. Not only are we accumulating positive area, but the rate at which we accumulate area is increasing, right? Because this function is getting higher and higher. It's getting further and further from the x-axis. So for example, let's say I was at 1 and I increased to 2, I'm going to gain all this area. But if I go from 2 to 3, look how much more area I gain. And if I go from 3 to 4, look how much more area. I'm gaining more area every time I increase. So not only is my graph increasing, the rate at which it is increasing is increasing. Okay, and so what my graph on the right side is going to look like is we're going to start at 0. Oh, I didn't want to zoom in. Let me cancel this. Do it again. So it's going to increase at an increasing rate, and I'm going to see something like that. Now on the left side, I get kind of the same story, right? The only thing we have to think about is if I'm going on the negative side of the axis, let's think about maybe G of negative 2. So I'm thinking about this area here. Well, G of negative 2 would be the definite integral from 0 to negative 2 of 1/4 t squared. But if you think about our properties of definite integrals, this is just going to be the negative version of negative 2 to 0. I forgot my dt's. And we know from negative 2 to 0, that's going to be a positive area. And so the negative of that is going to be a negative area. So basically what I'm trying to say is, even though the area is pretty symmetric on the right and left side of the y-axis, because of this property of definite integrals and the way that our bounds are going to be oriented on the negative side, we're basically going to see a reflection over the x-axis, and we're going to see something like this. And so when I'm thinking about, well, what's the graph of G look like, if I think about how I accumulate area and also account for these properties of definite integrals, I would suspect my graph looks something like that. So let's turn it on and see. Yeah, pretty close, right? Kind of like a cubic function here. All right, so what we're going to do now is we're just going to reset with a different function and try to do that same thing. See if we can kind of, from kind of an intuition point of view, sketch out the graph. Okay, so here is our new curve. You can see it's a sine curve, kind of messy, but no problem. We're just thinking about areas, and we're going to be very conceptual anyway. All right, so we're going to set A to be 0, and we want to think about accumulation. So we want to think about how much area has been accumulated from, I'm not sure why I've got this at 1. Kind of an interesting thing. But either way, we're not going to mess with Desmos, so I'm just going to draw this in manually. So let me get my little pen drawn up. Let's see here. If I'm starting A at 0, then again, my G function, the graph will start at 0 because, again, 0 width, right? If I'm starting at 0, ending at 0, that interval has 0 width, it's got 0 area. But let's notice that when we first start from 0 to 1, all that area is negative. So my function is going to start off going into the negatives. But then, about at 1, once we cross here, as we accumulate this area, this is positive area. So now I stop getting negative and start becoming more positive. By the time I get to 2, I should be at exactly 0. How do I know that? Well, just the symmetry of the sine curve, right? I kind of got that muddied up, but let's think about like here, and here, there's the exact same amount of area. So they should this negative area and this positive area should cancel each other out, so I should be back to 0. And then from 2 to 3, I'm gaining positive area. But then from 3 to 4, I'm gaining negative area, which is going to cancel out my positive area, and I should be back to 0. Again, just kind of from the symmetry of the situation. And we can kind of see what the pattern is going to be, right? I'm going to get a valley, back to 0. I'm going to get a peak, back to 0. And I could trace the same thing back this way, because if I go on the left side of 0, I get some more area. I get negative area, but again, think about those properties of definite integrals. Negative and the negative of a negative is going to be a positive. And so I get something that looks like this. I get this kind of, again, it's a sinusoidal curve. Maybe it's been shifted a little. Well, actually, if this is a sine, it's not been shifted at all. If it's a cosine, maybe it's been shifted by a little bit. But it's sinusoidal in nature regardless. So that's what I would suspect, just thinking about it from a point of view of accumulating area, starting at 0, going to the right, starting at 0, going to the left, and just keeping in mind that with integrals, things under the x-axis we call negative area, and obviously otherwise it's positive. So let's turn off my scribbles and see what Desmos has to say. Pretty much agrees. I didn't get the amplitudes right, but of course I didn't take a lot of care in getting the exact amplitude, so that's probably not a surprise. But you can see pretty much generally what we thought was going to happen. So when you see these sorts of accumulation functions a lot, especially if you are in, kind of in physics or the physical sciences, you see accumulation functions quite a bit. And like I said, I thought whenever I was first introduced, kind of non-intuitive. When you think about it from this more visual graphical perspective, I think they make a little bit of sense. I think about it almost like it's a fuzzy definite integral. And I say it's fuzzy because it's not like well defined the upper bound. That's free to vary. But anywho, that is accumulation functions in a nutshell. Again, hopefully whenever you run into them, you think about this Desmos demonstration. Think about it from a graphical perspective.